is the first review, which is physical and chemical changes, a little bit on measurement, not too much, but like density, percent error, stuff like that. And Sig Figs, everyone's favorite. We'll kind of wrap up with that. The next day, after all these, since this takes a while to like upload and process and do everything that needs to get done for it to be ready, I'll upload this video on my website tomorrow morning, in addition to sometime tomorrow practice problems that go along with everything I'm talking about in this video. So mainly these videos are just me going over examples and just kind of giving you a brief like, hey, remember this type of reviews, and then you can kind of practice problems on your own. The key will be up to those practice problems as well. And as usual, you can come approach with any questions that you may have. As usual, you can text me on Remind during this if anyone's even tuning in. But I'm not really paying attention to how many people are watching. So even if there's no one watching right now, this will be up and ready to look over at any point starting tomorrow. So I'm going to start with physical and chemical stuff. I'll just kind of break down like the very beginning of the year, the stuff that might seem kind of just not pay attention to and be careless about on the Regents. Get those like easy questions wrong because you weren't focusing on that, because you know that you struggle with solutions or you struggle with moles. So you're like, oh, I'll be fine on everything else. And there's like a little bit of the stuff we did way back when that is, like I said, easy in nature, but you just haven't been paying much attention to recently. So generally speaking, when we go into chemistry, we're talking about matter, which in this class we kind of just break into what we call a pure substance and a mixture. Ran out of room there. That's okay. So we have pure substances and we have mixtures. And the pure substances we break down furthermore into two things. We have elements, and they can be elements that are what we call monatomic, which are elements that just kind of exist as in one atom. So, you know, like any of your metals, Mg, Na, etc., they're all monatomic elements. In nature, it's just one type of atom involved. And then you have your diatomic, which are, when you find them in nature, those are your Brinkelhoffs. Brinkelhoff, Brinchlhof, are all diatomic in nature, meaning there's two atoms. So H2, Br2, etc. So anything involved in Brinkelhoff is what we call diatomic. All right, so you have elements. They can be monatomic, they can be diatomic, and then you also have compounds. And I'll break down mixtures on the bottom somewhere because I'm going to run out of room. And your compounds are just two or more different elements. All right, so we've been working with compounds for so much this whole year. Ever since this unit, ever since we've been doing like chemical changes, we've been talking about compounds a lot. So anytime you just combine two more different elements, you know, CO2, NaCl. I'm not going to go over the types of compounds. We're not focused on like molecular and ionic today. Just this is very straightforward. What is the first thing we started doing in this class? Review. So just take two different elements, throw them together, and you have a compound. And then you have, and so actually before I go on to mixtures, all of these are chemically combined. You cannot separate these physically. An element, you can't separate any more than what it is. When you have Mg, that's Mg. It's made up of Mg atoms. You cannot break that down any further. Compounds, you can break these down, but you can only do it chemically. So you can't just filter away the carbon out of CO2. You can't just filter away distill the oxygen out of carbon dioxide. You have to chemically separate a compound. Then you have your mixtures, which we define as either homogeneous and heterogeneous. So your homogeneous mixtures are those mixtures where when you look at them, you can't really tell they're a mixture. Like if you had a little bit of salt dissolved in water next to a cup that was just pure water, probably at first glance, you couldn't be able to say, oh, that one's the salt water and that one's the regular water without just tasting it. So homogeneous mixtures, we say, are uniform particle distribution. So the particles are just distributed uniformly amongst each other. And when I draw particle diagrams in a minute, you'll see what I'm talking about. Versus a heterogeneous mixture are not uniform. So a heterogeneous mixture, a classic example, is just like oil and water. A pepperoni pizza. You can see the pepperoni. You can pluck it off. You can see the cheese. You can peel that off. You can see the tomato sauce. You can scrape that off, etc. Versus a homogeneous mixture is something like salt water. That salt dissolves in water. You can't really tell that there's salt in it. So it's distributed itself uniformly throughout that mixture. So we call that a homogeneous mixture. Heterogeneous mixtures, so both of these can be separated physically. So these are physical combinations. They are not chemically combined. All mixtures are physical in nature. So something like a heterogeneous mixture, like let's say sand and water. A lot of heterogeneous mixtures, you can just filter the substances apart in some way. You can filter out the oil from the water. You can filter out the sand from the water. You can do a lot of different things to separate them just by simple filtration. Versus a homogeneous mixture, you really can't use filtration. Like salt water, if you try to filter out the salt, like put some filter paper in a glass or in a funnel and just pour salt water onto the filter paper, the salt water is just going to pass right through because it's uniform in nature. So homogeneous mixtures will evolve a lot of techniques because a lot of the mixtures we really end up talking about in here are mixed with water. They're all aqueous. A lot of homogeneous mixtures are AQ or aqueous, which means it's dissolved in water. So usually just boiling off the H2O, separate that liquid from the solid, or you can use a process called distillation, and this is for a liquid mixture. So let's say you mix alcohol and water. How do you separate the alcohol from the water? Well, the whole point of distillation is that two liquids, as long as they're different liquids, boil at different temps, different temperatures. So let's say water boils at 100 degrees Celsius. Alcohol boils at a little under 100. If you know that alcohol boils at 97 degrees, let's say, you can boil off that alcohol at 97 degrees and it'll evaporate and recondense in this tube, and you'll be left with pure water in one flask, and then the alcohol after it's condensed again in another flask. So, those are mixtures. These are the main ways we see a lot of things, a lot of questions about separating mixtures. Heterogeneous, you use filter paper, or they call it filtration. Homogeneous, you can separate just by like boiling off one of the liquids, or the more proper term would be distillation. The other thing you're going to see a lot is particle diagrams. This is from a while ago. So this is when you have to like draw in a box you know, what does this element look like as a liquid? What does this element look like as a solid? So I'm going to start with drawing particle diagrams of the different phases: solids, liquids, and gases. The key thing you want to do is have these particles in like a structure. In like most solids occupy like crystal structures. You don't want them to occupy the whole bottom of this container I'm drawing here. Just imagine you took like a block of ice and put it in a big box. It's just going to fall to the bottom and stay there. It's not going to spread out. That's what you kind of want to draw when you're trying to draw a solid. So solids, I'm just going to color them in so it's easier, kind of maintain this rigid structure. It's there. It's not occupying the whole volume of the container. It's not occupying any of the space. It's just you take a solid, you drop it in there, and it plops to the bottom. A liquid, the key with a liquid is you want to take this solid here and just take those particles and just kind of spread them out along the bottom of the container. Just like imagine you're just pouring water into a bottle. If you pour it halfway up, it's going to go halfway up and stay there, but it goes from the bottom up. Not that it really makes a difference when we're grading these things, but I see a lot of people trying to draw liquids like floating in midair. And we work really hard to work with what you're drawing, but sometimes it's hard to tell if you're drawing a liquid or a gas when you do that. So imagine just taking that solid and just taking those particles that are nice and stacked and rigid and just kind of moving them across the bottom. So I'm going to draw those 9 particles again as a liquid. And they just kind of spread out. They're not in this like compact, rigid structure. They're occupying whatever volume that you've allowed them to occupy, whatever space that you've allowed them to occupy there at the bottom of the container. And then they stay there, much like the solid.
Can I have your phone, Mr. G?
Why? What's up?
I just need it for the Apple remote.
Yeah. I need it back, though, because I have like an outline of what I'm talking about on here.
Fine.
So play whatever you want to play, and then...
BRB.
Thanks. So, that's a liquid. A gas, you want to take those liquid particles and just... Whoa, what did I do? Spread them out. A gas occupies the entire container. They occupy the entire volume of whatever container they're in. You know, just spread them out all over the place. You don't have to necessarily be far apart. A lot of people think like solids and liquids and gases, the key is, oh, just make them further apart. Not always the best way to do this, because like water as a solid, like when water forms ice, the particles actually expand a little bit, and they're further apart as a solid than liquid water. And I know that sounds counterintuitive because it is, but it's true. So the key is a solid, you want that like rigid structure. The liquid, you kind of want to just like collapse that structure and occupy the space at the bottom. And the gas, you just want to take over the whole container. So that's what gases do. Regardless of how much gas you have, even if you pump a little bit into that container, like the most minute amount, they will spread across everywhere. So these are your phases, and you can draw these phases for anything, elements, compounds, or mixtures. So what do the elements look like in a particle diagram? An element will look one of 2 ways. You can have a monatomic element, like for example, if you were drawing Mg, let's say as a solid, Mg is monatomic, so you just take one atom and just kind of draw it as a solid. And I just kind of started over on the left-hand side for whatever reason. But either way, it doesn't matter where you draw it, as long as it looks like a solid. Or you can also draw a diatomic element, like let's say N2. So N2, since it's diatomic, you have to make sure that those 2 atoms of N2 are the same color / not one. Both of them are either shaded in or not shaded in, because those particles are both representing N. And since it's a gas, you're just going to kind of draw them occupying the whole container. But Mg here was a monatomic element. It was 1 circle on all these circles are just kind of connected and stacked and rigid like a solid. So a monatomic element you represent using 1. So a monatomic would look like that, or just like 1 particle. And then a diatomic either is like that or both shaded in. Do not make them different colors. If you have an unshaded and a shaded together, like this, that would be a compound. Because they're two different, since they're two different colors, they're represented by 2 different types of atoms. And that by definition is a compound. I mean, there's a variety of questions they can use with this. So I'm just drawing like the basic, what do elements look like? Will look like a monatomic magnesium or a diatomic nitrogen. Compounds can be a variety of things. So they can be 2 different atoms connected together, or you can have like H2O, 2 H's, 1 O, or you can have like CO2. So there's CO2. You draw like that. And the orientation doesn't matter. You can draw them any which way. So like the fact that I just drew CO2 diagonally, I could have drawn it like this. Right? They're moving. These particles are always moving around as long as they're not at absolute 0. So they can rotate, and that's okay. And obviously compounds can get crazier than this. You can have like 5 different atoms bonded together or whatever, but typically they're not going to get much more complicated than what you see here. They either have those diatomic compounds, 1 atom of C and 1 atom of O, or those triatomics where 3 different atoms or 2 of the same, 1's different, etc. So if you're going to draw, let's say, well, I'm going to do CO2 as a liquid. Why not? It doesn't really matter. You're going to kind of just draw these carbon dioxide compounds somewhere along the bottom, not forming that rigid structure, but not occupying the entire container like a gas would. I know it's hard with compounds, but they usually will only ask you to do these particles, so it's not getting overcomplicated, and we're like really looking at it saying, is this one, are they kind of touching? Is this solid? So, you know, they'll say like draw 4 to 5 particles of CO2 as a liquid, or of CO2 at this phase in this heating curve, or whatever. So that's a compound. It's how you approach these problems is no different than how you approach drawing an element. It's no different than differentiating a solid, a liquid, and gas. It's just being careful that when it asks for a compound, you draw a compound. And then the last is a mixture. And you can have like 3 different types. You can have a mixture of elements, which would look like this. So I'm going to do a mixture of Br2 and Na. So Na, since I know it's a metal, let's say we're at STP or whatever temperature it is, Na I'm going to draw as a solid, because Na is sodium, and I know sodium is a metal, and let's say we're at 300 Kelvin. And then bromine, I think at 300 Kelvin, that's starting to turn into a gas. But let's assume we're at a temperature where bromine's a gas. It's diatomic, and I'm going to just draw it like this. So that would be a mixture of elements, where I have my diatomic bromine floating around, and then just solid chunk of metal sodium just sitting right there. And this is an example of a heterogeneous mixture, because since that solid chunk of sodium is just sitting at the bottom, I can just go in and pluck it out without having to like boil off anything or use any complicated processes. Sodium, and it's not distributing itself evenly and uniformly amongst the bromines. I can just kind of pluck that out. You can have a mixture of compounds. So a mixture of compounds, you can do like, again, this really doesn't matter. You can do H2O and CO2. So let's say we have dissolved carbon dioxide in liquid water, made seltzer. The waters I'm going to draw as a liquid. So the waters are going to kind of just be distributed along here. And since the carbon dioxide is dissolving in the water, I'm going to draw the carbon dioxide distributing within the waters. So you notice how the carbon dioxide is floating all over the container here. I am trying my best to accurately represent this as a homogeneous mixture. I have my waters, which I've represented with this Mickey Mouse looking thing, and the carbon dioxide, which I've represented as whatever that looks like. I don't know. Doesn't matter. And like these carbon dioxides here, I'm like drawing them distributing throughout the whole container. They're not just staying at the top, kind of separating an oil and water type barrier like a heterogeneous mixture would. So I would consider this homogeneous. Now, if you're worried about the Regents, like how do I know to draw this as a hetero or homogeneous mixture? You got to keep in mind, all these Regents questions typically ask you to have one thing to do, one task, 1 point's worth of work. So there's either going to be some sort of hint in the problem that it's a heterogeneous mixture, or the fact of how you draw it as being homo or heterogeneous for that question might not matter. But when you see questions involving mixtures and particle diagrams, like when I post these questions on my website tomorrow, just feel free to see what kinds of questions they're asking. Usually, they're not going to try to overcomplicate and ask you to do 2 to 3 things at once. If they want a particle diagram of a mixture of compounds, draw it that way. If it asks you to draw that mixture a certain way, it's highly unlikely, but just take your time. Make sure you show that they're both not interacting with each other, but they're not forming like separate layers like a heterogeneous mixture would. They are distributing themselves amongst themselves, what we call uniformly. Last particle diagrams and compounds. And again, that could be whatever. Let's say you want to do N2 and H2O again. N2 is a diatomic element, so I'm going to draw it with open circles this time. I don't know if I drew it with closed before. I didn't draw N2. So. And then water will be the same Mickey Mouse looking thing. And we'll have a little container. And water I will again represent like this. 2, I'm going to draw it as a homogeneous mixture again. N2 is distributed amongst the water molecules. Yeah, I'm trying to make this look like a water down here. That's a water. Water. And that's it. So that's a mixture of an element and a compound. There's a lot of variety of questions. I highly encourage you practice doing questions with particle diagrams. I'm going to star this. It's one of the more... one of the first, I would say, difficult things we encounter. Hard. It's just easy to do it incorrectly. You will underthink what you need to do. You will say, "Oh, I've drawn particle diagrams before. This is fine." And even if you talk to a lot of AP chemistry teachers, a lot of students will just kind of struggle drawing these particle diagrams. They are oversimplified in their eyes, and they just kind of say, "Oh, this is fine," and they just don't they don't take a lot of time to think about what the question's asking. So just remember, is it asking you to draw an element, a compound, a mixture? Is it asking you to draw it as a solid or a liquid? These are all things to kind of keep in mind as you draw this. And most students do fine with these, but they really, year after year, and you can talk to any of your chemistry teachers, I think that is historically one of the hardest ones to draw. But that's just me. All right, I'm just kind of looking at my outline here, what we're doing next. So we talked about physical and chemical changes. We talked about the compounds that you can separate physically. We didn't really talk about chemical changes. So the key with a chemical change I might save this for tomorrow. Actually, let me see if we have time at the end. No, we'll talk about it now. We'll talk about it now. Physical change. Keep changing my mind. Physical change. You change your state of matter, but you do not change the substance. The substance will stay the same. So that's just like taking H2O as a solid and melting it to form H2O as a liquid. I still have H2O. That has not changed. All I did was change it from a solid to a liquid. That's a physical change. So most of these you can easily reverse. They're reversible. I can go back this way and just freeze liquid water and turn it back into a solid. So the physical change, you just change your state of matter. Melting, all of this stuff. Solid to liquid. Actually, let me draw two separate ones. Liquid can go to a gas. And then these are the ones that we tend to forget. So, solid to a liquid, that's melt. Liquid to a solid, that's freeze. That's a Z. I think you can pick up on that. Liquid to gas, that's, we could call it a few things, but evaporation. Call it boiling, vaporization, any of those. Gas to a liquid is condensation, or it condenses from a gaseous water vapor to liquid rain. And then solid to a gas is that fun word called sublimation, which was on one of your CASA learnings that some of you still have to do. And then a gas to a solid is called deposition. It deposits. You take a gas and you just take steam and you funnel it out into negative 100 degrees Celsius. It's just going to turn into a solid immediately. So it deposits as a solid. So these are all your physical changes. These occurring, that's a physical change. A chemical change is when you actually, physically, not physically, I shouldn't say that. You change your substance. So the substance, whatever you're working with, completely changes into something new. Typically, we would consider these irreversible, though some of them, if you take water and split it into hydrogens and oxygens, there's nothing stopping you from reacting those hydrogens and oxygens back to water. But a lot of them are irreversible. So stuff like burning, keywords would be like burning, running. If you see a bunch of options and you see something like H2O changing into H2s and O2s, now that's H2O. This is water. This is hydrogen, which is an explosive gas. This is oxygen, which we breathe in to survive, but is also an explosive gas, very different from at room temperature liquid water. So these things are just irreversible. You're forming something new. Bubbling, energy is produced or consumed. And you see the change. So not just inputting energy to melt water, but you don't really do anything. You just mix two substances together and then you feel that container get hot or you feel that container get cold. Spontaneously, we say. So if you just mix two things together, all of a sudden they start to feel this heat being produced, or you feel this coldness, you feel this heat disappearing and it gets cold. That's a chemical change. So not you putting it on a hot plate. And then some color changes are, but mainly with the stuff from table F, when you mix two things together and they turn that mustardy yellow or that kind of opaque white, that kind of color change. Food coloring is not a chemical change. Off the food coloring. So look for, there's really questions as simple as, is this a chemical change? And you look at the options and one says melting and boiling and freezing, and then something about burning and bubbling and the color change and energy being consumed and stuff like that. So these are just keywords for chemical changes. Yeah. Okay. So next, I believe, was some measurement stuff. So let's look at the reference table for a sec. There's a few things that be helpful. Table C has all the metric measurements prefixes. To me, it's a little confusing. I'm not a big fan of Table C, especially since it's so rare to see questions involving micro, nano, and pico. But at the way beginning of the year, I just said take these numbers and kind of convert it into, and don't forget to fill in the gaps in the middle. So 10 to the third is your biggest one, which is kilo, and it goes all the way down to pico at 10 to the negative 12th. So 10 to the negative 12. Let me change the size of my pen. Okay. And then so you want to go from 3 to negative 12. So I'm just going to fill those in. 2, 1, 0, negative 1, negative 2, negative 3, 4, 5, 6, 7, 8, 9, and 12. This is the only way I've thought to use this table effectively. So this is 2, 3, nope, not 3, 1, and then we get to our base units, which is 0. So anything involving grams, meters, liters, even joules will be your base unit of 0. Then you have deci, centi, milli, skip, skip, skip. So this is 4, 5, negative, negative. Micro, negative 7, negative 8. Nano, negative 10, negative 11. Pico at negative 12. So if you're ever asked to do a conversion, just kind of count. If you're counting to the right, if you're moving your number line to the right, your number's going to slowly get bigger and bigger and bigger. Bigger and bigger and bigger. And if you're moving your number from a unit on the left, from a unit to the left, your number's going to get smaller and smaller and smaller. So if you're converting meters, let's say 1,000 meters, I'll do it to kilometers and micrometers. So for a kilometer, I'll do that in red. You take 1,000 and you went 1, 2, 3, 1, 2, 3. So that's 1 kilometer. And then I'll just rewrite this with 1,000 again. Or if you're converting 1,000 micrometer, I'll do this one in green. You go 1, 2, 3, 4, 5, 6. So move that over 1, 2, 3, 4, 5, 6. Fill that all in with zeros. 5, 6. And then that's a big number. 3, 1, 2, 3, 1, 2, 3. Is that a trillion? A billion micrometers? So, like I said, converting with these is not a popular topic. There's a lot more chemistry, I think, that's a lot more important for us to make sure we get on the Regents. But they might pop up. The biggest ones I always see are milliliters to liters, and vice versa for your molarity equation. Give you milliliters, and they want liters for your molarity equation, and that's just divide by 1,000. So take your milliliters and divide by 1,000, or take your milliliters and go to the left 1, 2, 3 times, which is dividing by 1,000. But anyway, I don't want to focus too much on metric conversions because there's a lot more other important stuff. And let's look at the time. Almost done. When I'm done posting these on YouTube, I'll have direct links in the description that says I started talking about Sig Figs here, and I talk about the metric system here. So if you're watching this video and you click it and you're like, oh my god, is this an hour? If you just want Sig Fig help, click on the one that says Sig Figs, and then it'll just... Table D is helpful. These are all units. Sometimes there's literal questions that are like, what unit of the given is a unit for heat? Check table D. Probably has the answer on it. So it'll be joules. And the other options would be like Kelvin, which is the popular wrong answer because that's temperature. Molarity, whatever. So check here for units. This is good to know. This is good to know that it exists. Equations in this unit we got density. Mass is going to be grams. Be liters / centimeters cubed. Or usually milliliters. But volume, liters is also a unit of volume. So then you need to be able to find all of these quickly. Use the equation given, or draw the lovely density triangle, which I'm not a fan of because I don't like tricks. I would prefer that you did some algebra, but no, mass is up top. So you don't even know the triangle that well because I hate it so much. But kids like it, so mass, volume, density. That should be it, right? Yes. So mass divided by volume. So cover up. Let's say you're trying to solve for density. So I'm just going to cover that up. I don't know how else to cover it up. You do mass divided by volume. That gives you density. And let's say you're trying to solve for volume. Well, you do mass divided by density, and you'll get volume. And if you were trying to solve for mass, you just cover it up. Density times volume, and that'll give you mass. Times. So this was mass. So mass divided by density gives you volume. Mass divided by volume gives you density. Density times volume gives you mass. And then percent error is pretty straightforward. Percent error, most students get wrong because they don't take their time reading. So measured value is whatever you get from your experiment. Like you conducted an experiment and you calculated the density to be 5. According to table S, the actual or accepted density is 3. What is your percent error? 5 minus 3 divided by 3 times 1,000. Students just get lost in the wording. It's not a hard equation, but keep in mind, what did you calculate? That's measured. What is the actual value? That's accepted. So if you calculated the density of water to be 0.8, and you know the density of water is actually 1, you do 0.8 minus 1 divided by 1 times 1,000. I would say for your final answer, take the absolute value. I encourage my students that it's okay if you get a negative or positive number, because a positive number means you overshot the actual, and a negative number means you undershot the actual. But usually when I see these questions on the Regents, they're all positive numbers, even if you calculated it to be negative. So take the absolute value of it at the end so it becomes positive. All right. Last thing I want to talk about is Sig Figs. Yay, everyone's favorite. So we'll do the rules of what numbers count first. 1, non-zeros are always significant. Period. Always count your non-zero numbers. 2, sandwiched zeros. Meaning zeros that are in between non-zero numbers. These will always count, regardless if there's a decimal or not. Those zeros count. And then 3 is always the hardest one to explain, that I've found myself trying to simplify as much as I can. But the only other time a 0 will count is if A, the number contains a decimal, anywhere. I don't care where that decimal is. If there's a decimal in that number, somewhere, beginning, middle, end, go to B, circle non-zero, and count everything after. Cool. So usually I find myself with 3, just giving as many examples as possible to make that as clear as possible. So I'm going to write down a bunch of numbers, and I'll go over how many sig figs are in each. So 1,000, 0.001, 1,000 dot, 1,000,000, 200, 0.50100, 6.500. Okay. 1,000. Non-zeros always count, so that 1 counts. Sandwich zeros always count. There's no 0 sandwich here because it doesn't end with a non-zero number. The non-zero or the zeros will count if they come after a non-zero when there's a decimal. There's no decimal in this number. So 1,000 has 1 sig fig. 1,200,000. Non-zeros always count. There's 2 non-zeros. Sandwich zeros always count. There are 3 sandwich zeros, so now we're up to 5. The 1, the 2, and the 3 non-zeros. These zeros count because they are not sandwiched and the number does not contain a decimal, so we don't even worry about those. This number contains 5. Number 3, 0.001. We have a decimal. So, find your first non-zero, circle that non-zero, and everything that comes after that non-zero is significant. Nothing comes after that non-zero. Those zeros come before that non-zero. This number has 1, just the non-zero. I'd go into a big explanation of what sig figs mean and why we use them, but I think that's just a waste of time at this point, so let's just go into the rules. 0.50100. We have a decimal. Find the first non-zero number. Circle that non-zero number and count everything after that non-zero, including that non-zero. These zeros are not sandwiched, but that does not matter because we have circled the non-zero number in our decimal and we are going to count everything after that non-zero. This has 5. 5, 1, and the 3 zeros all count. 1,000 dot. Again, does not matter where the decimal is. Circle your non-zero and count everything after. This has 4. All those zeros count. 6.500. Circle your non-zero because there's a decimal. Count everything after. This has 4. That's the only foolproof way I've thought of that simplifies this as much as I can. I know a couple teachers do like Atlanta and Pacific. Then I'm like, well, if you're in a test, what if you panic and forget where the Pacific Ocean is? And I don't want to play that game. So if there's a decimal, circle the non-zero. That counts. So does everything after it, regardless of where the decimal is. Decimal's at the beginning, find the non-zero, go. Decimals at the end, find the non-zero, go. Decimals in the middle, find the non-zero, go. All right, let's do adding and subtracting. Take all your numbers and line them up so the decimal is all in the same place. So let's say you were adding 6.53 plus 7.012 plus 8.1. No. I'm going to do 81. Okay, so the decimal will be right here in 81. If the decimal is not given, it's just at the end of the number. So I'm going to put 81 up top, even though it didn't come first, that's okay. And then line up all the other numbers so the decimal hits at the same spot. Okay, when you're adding or subtracting these, it does not matter which. Your answer needs to stop where all of your decimals are lined up. So your answer needs to stop right here, because that's where all the decimals line up. So you're going to round. So let's add all these up first. So I do 81 plus 6.53 plus 7.012, and I get 94. Hopefully I added these up right. That'd be weird. 0.542. Okay, so I have to stop my answer at the ones place, because that's where they all line up. And I'm going to look here to see if I need to round that to 95 or keep it as 94. And since it is 94.5, the rounding rule is 5 or higher, go up, 5 or less, go down. I'm going to round my answer to 95. Now you can put the decimal there if you want, but it really doesn't matter. So the amount of sig figs in adding and subtracting, not important. Line up the decimals, add them up or subtract them, and round where you've lined up the decimals. People are going to want to push boundaries here and say, but it's 94.54. Do you not round because it's 54? No, you round, because you're just going to round. You're going to look right here, the number right next to it, and then round up to 95 if it's 5 or higher. Keep 94 if it's below 5. Multiplication and division is all about how many sig figs are in my number. So I'm going to do very similar numbers to what I just chose. I'm just going to change it up a little bit. 6.53 times 7.012 times 80. We're going to get a weird answer for this, and that's okay. I'll do another example because these tend to be the harder ones. Your answer will have the same amount of sig figs as the least amount of sig figs in the numbers you're multiplying and dividing. So 6.53 has 3 because they're all non-zeros. 7.012 has that decimal, so you're just going to count everything after. This has 4. 80 has 1. So your answer needs to have 1 sig fig. So I'm going to multiply these together normally. Oops, didn't mean to do that. I'm going to multiply these together normally and then show you how I rounded it. I think I might have just got a question. Let me see. Third block. We have an open spot in our squad. It's going to just ignore that. I could have sworn I just got a text. Maybe not. All right. So I'm going to multiply these normally. Now, you're probably never going to see anything this complicated. Usually it's just 2 numbers. But I'm choosing an odd one just to show how to round it. 6.53 times 80. So I get 3663.0688. And I need to take this and make it 1 sig fig. Because 80 only has 1 sig fig. So I'm just going to take this 3 here. Notice that there's a 6 right after it. I'm just going to round this up to 4,000. No decimal. And that has 1 sig fig. Nine times out of 10, what have I seen a lot on the Regents? They ask you to do a density problem with the right amount of sig figs. Sometimes it just asks you to identify how many sig figs are in a given number, like up here. Sometimes I've barely seen a sig fig. But usually they'll say, like, this weighs 5.03 grams. It has a volume of 1.4 liters. What's its density? So you do 5.03 divided by, let's say, milliliters. 1.4 milliliters. Not that it makes makes a difference, but if I do 5.03 divided by 1.4, I get 3.592. But 5.03 has 3 sig figs and 1.2, so I need to round this to 2 sig figs. So I'm going to box in my 2. I'm going to round this up to 3.6 grams per milliliter because of that 9. That 9 is bigger than 5, so you got to round up the 3.5 to 3.6. That is it. So we went through kind of a lot tonight, so just like a quick recap. I'm going to post this on my website tomorrow. We had phases of matter, or states of matter, or types of matter. I don't even know what I'm saying. We can have pure substances or mixtures. Our pure substances are elements and compounds, where our element is either one atom or 2 of the same atoms combined, where we call one atom monatomic and 2 diatomic. A compound are 2 or more different elements bonded together, such as carbon dioxide or sodium chloride. These are all combined chemically and therefore can only be separated chemically, except elements. Elements you cannot chemically separate any further. Magnesium is magnesium. You cannot break that down into something else. Mixtures can be homogeneous or heterogeneous, where homogeneous are uniformly distributed particles, such as salt water, and heterogeneous are not uniform, like a pizza. These are physical mixtures. They're physically combined. That means you can separate them physically and not chemically. So physically, you can separate most heterogeneous mixtures using filter paper. Homogeneous mixtures, however, can't be filtered that simply. You can boil off the liquid if you have a liquid-solid mixture, such as salt water. You can boil away the water. Or if you have a liquid-liquid mixture, like alcohol and water, you can boil them at the lower boiling point of the other substance. So if alcohol boils at a temperature lower than water, you can distill it using distillation, and that will boil, let's say, at 90 degrees. The alcohol will vaporize, then decondense in a tube into another flask, and then you keep your water in your first flask since water boils at a higher temperature. We reviewed some particle diagrams. Solids, liquids, and gases. Solids are rigid and contained where they are. Liquids can occupy that space at the bottom, but not the entire container, and gases will occupy the entire container. Elements can be drawn monatomic, like magnesium, which is just one type of atom, either an open atom or a closed one, or diatomic, like nitrogen, which can be, again, drawn as 2 open ones or 2 closed ones. You can draw compounds, which are 2 different or more atoms combined. So you can draw something like sodium chloride in the left there, or water/carbon dioxide in the middle or the right. I drew carbon dioxide as a liquid here. You can also draw mixtures. So you can have a mixture of elements. Again, you will notice that these are all made of the same type. Na is at the bottom, and there's only Na atoms because it's just one type of circle. And then the diatomic bromine is represented with 2 of the same types of circles because they are both bromine. That is a heterogeneous mixture that I drew because the bromine and the sodium are staying separate from each other. You can draw a mixture of compounds. So I attempted as best as I could to draw carbon dioxide dissolving in water here, like it does in your seltzer. This is a homogeneous mix. Carbon dioxide and the water are distributed amongst themselves. They are mixing uniformly. You can draw elements in compounds, and I drew a diatomic nitrogen with a compound of water. And again, this was homogeneous because they are distributed evenly and uniformly. Physical changes just change your state of matter. They are easily reversible. You can melt, freeze to go from a solid and liquid. You can condense and evaporate to go from a liquid to a gas and vice versa. And you can take a solid and sublimate it to turn it into a gas, or go through deposition to go from a gas to a solid. Chemical changes will change the entire substance, and they are usually considered irreversible. You can burn things, rust, notice bubbling, notice energy being produced and consumed without you inputting any energy. you will see a color change. These are all evidences of chemical changes. You can have an example here where I took water. Water is a H2O drinkable safe liquid at room temperature. If you decompose it into hydrogen and oxygen, they both turn into gases, and they are both very easy to explode. They are flammable. Don't bring a flame around hydrogens and oxygens like this. So you take something and change it into something completely new with different properties. Sig Figs. Non-zeros will always count. Sandwiched zeros will always count. And then if the number contains a decimal, find your non-zero number wherever the decimal is. Find the first non-zero number as you read it from left to right. Circle it and count everything, including what you circled. 1,000 had 1 because it had no decimal and those zeros do not count. Only the 1 counted. 1,200,000 had 5 because the 1 and the 2 counted, and then the zeros were sandwiched in between that 1 and 2. The zeros after the 2 did not count because they were not sandwiched and there is no decimal. 0.001 only had 1 because the only first non-zero we see is at the very end. So the zeros before that 1 don't count in this decimal. 0.50100 had 5. We circled the 5 because we had a decimal in our number and 5 was the first non-zero we saw. We circled it and counted everything after it. 5 and the 4 numbers after it add up to 5. 1,000 dot had 4 because now we have a decimal, so we have to include that 1 and everything after. And 6.500 also had 4 because we have to include that 6 and count everything after. Adding and subtracting numbers to the correct amount of significant digits. Line up all the decimals so they line up together perfectly. Box that in. Your number will stop where those decimals line up. So we stopped at 94 because our 81 stopped at the ones place. We rounded up to 95 because it was 94.5. So that 0.55 is a 5 or higher, and you round up. So we rounded up to 95. Multiplication and division. You need to count up the total amount of sig figs in each of your number and then round to that sig fig in your answer. Since 80 only had 1 sig fig, just the 8, our answer must only have 1 sig fig. This was a little complicated. So I did another easier one. 5.03 divided by 1.4. 1.4 only has 2 sig figs, so we must stop at 2 sig figs. We got 3.59. That 9 tells us to round that 5 up to a 6. That's my story, and I'm sticking to it. I'll see you tomorrow night. Tomorrow, we are doing gas, heat. See you then.